Okay, hello. This is Mitchell, and I've been doing some of the Project Euler questions, and this was one of them. This is problem 32 of Pandigital products, and the question is, as you can see on the screen. Now, I've been using Python to solve a lot of these questions. This one here, I arrived on the answer a few weeks ago of 45,228, and the question involves these pandigital products where they contain one digit from 1 through 9 for it to be called pandigital, and you can have the product as well as the answer containing these numbers. I was doing some research obviously on this question before I had solved it, and I'd found a video like this, for example, which is very complicated. Here you can see it's over 40 lines of code as well. It took a very long time for this gentleman to reach the answer. So I thought there's got to be a better way than this, and this is what I come up with. It's only 16 lines of code. It runs nigh on instantaneously, so I just hit run and there's the answer. The way I managed to do this was mainly using sets as well as basically a bit of string manipulation. So before we even start programming, we need to really understand what kind of possibilities of a pandigital number we can get. So if I just come down here for a moment, if we imagine that we have a product and an answer, well, we know that the length of the first product, if we call that A, as well as the length of the second product, excuse me, and we'll call that B, that must also, as well as the length of the answer, if we call that C, those must equal 9, because they need to have every digit 1, 2, 3, 4, 5, 6, 7, 8, 9. So the length of, if you added up all those together, would be 9. So this is the kind of equation we've got, the two products and the answer, and the length of those must be 9. So what kind of possibilities could we have? Well, we could have a 1-digit number, for example, with a 4-digit number, which would also give us a 4-digit number, right? So imagine this D is for digits. So yeah, for instance, 1,000 times 2 is 2,000, and because you can only go up to 9, even 9 times 1,000 will still be a 4-digit number. It'll still be 9,000. So that's one possibility. Sorry, excuse me, this should be a 1. Yeah, 1. So a 1-digit number with a 4-digit number is always going to give us a 4-digit number. And the other possibility, and before we move on, if we note there that 4 plus 4 plus 1 is 9, the other possibility is a 2-digit number. And now instead we drop the number here, and we obtain a 4-digit number. Yeah, this is the other combination. Simply all we've done is we've took a 1 out of here and put it into here, right? That's the other possibility, and if we do the same again, we'll just loop the other way around. So imagine we took a 3 and put it into the 2, it would be a 3-digit times a 2-digit equals a 4-digit, which of course we already have, and if we did it again we would loop the top line. So they're the different outcomes that we can have, which is represented by these 4 loops here. So this for loop will represent every 1-digit number, and this one here represents every 4-digit number. This one here will define every 2-digit number, and this one here will define every 3-digit number. So what these for loops are doing is it's taking every single possibility of every 1-digit and 4-digit number and running them through a function which we'll explain in a minute called the test, Pandigital test, where it will take the two numbers, test if the product and answer is Pandigital, and the same here, but instead of every possibility of 1 digit and 4 digits, it will become every possibility of 2 digits and 3 digits. So these for loops here significantly reduce the time it will take to compute every single possible number combination, because we know what digits we're limited to. If we didn't know this, we'd have to just simply run a loop that continuously increments, and you wouldn't really know an upper limit. Or your upper limit would be when the length of the number is 9. But there's lots of numbers in that range that aren't going to be Pandigital. This severely decreases the range, so it's nice and fast. So before we move on to defining what the test is, I should explain to you why we have used sets. So if we imagine every product, because we're running through every value of A and B, we could run into the same Pandigital product many times. Because we are using sets, it will mean that any duplicates, so if we get the same Pandigital number twice, even if we add it to the list, which is what this line here does, it will not add it twice. For example, if the number is already in there and we want to append a number but it says it already exists, it will just simply not add it. The set will only ever hold one value of that kind. So on the problem itself here, it does, I believe, say some products can be obtained in more than one way, so make sure to only include it once in your sum. So this line here is the exact reason that we use sets. We only want it to exist once, so this is why the set is used. So yeah, so now really onto the difficult part of the question. So obviously we've got our digits, we're trying out every different combination. We now just want to move on to actually testing whether or not it is a Pandigital number. So the way we would do this is we have to see if all of the numbers only occur once and it goes 1 through 9. We can actually use sets again here because, for example, a set has no order, and again it will only add a number in once. So if the length of the set is 9, we know that every single number has been used once if we take each individual part as a string, which is exactly what this line here does. So first of all, we check if the length of the first product, the length of the second product, and the length of the final product all adds to 9. We described that earlier. This would mean it's one step closer to being Pandigital. Of course, we need an extra constraint, which is this part here, because for instance you could have a product which is 1, 1, 1 9 times. I believe this is 9, 7, 8, 9. So this would pass this first constraint, which of course we don't want. That is clearly not Pandigital because it only ever uses one digit. So the way that we check that it's used every single digit is if we put each of those numbers into a set. And what this will do is, for example, let's say string 1 was 1 and 2, string B was 3, 4, 5, and the product was 6, 7, 8, 9. What that will do is it will put all of those together, so all this string combined together would be just simply the letters 1, 2, 3, 4, 5, 6, 7, 8, 9, and it will put all of them into a set. And remember, if the number exists many times, it will only add that letter in once. So for that example with 1, 1, 1, 1, 1, 1, and so on, that will only ever add one singular letter or number 1 into the set. So therefore that set would not equal this set here of 1, 2, 3, 4, 5, 6, 7, 8, 9. If it uses 1 of every digit and the length is 9, then it will satisfy this if statement and it will add the number well, more importantly, the product, because it's only the product that we are interested in here. Just what's the product? Then that is what we will add to the list, and this list is defined here. No, it's not a list, sorry, a sum. But yeah, so this will add this to this sum, this set, sorry, outside of the function, which is what we want. And when we do that for every single possibility, and it returns that it is pandigital, it will add it to this number. Once all combinations are exhausted, we'll have a set filled with only one of each pandigital number, won't have any duplicates, and we simply just print the sum of this like the question asked. As it says here, find the sum. And when you run that, you achieve the answer of 45,228. We can actually take a look at what this list actually looks like if we type in viable nums and we print that. We can actually see all the different products of the pandigital numbers, and it's simply this sum command is just adding those together and outputting the final answer. So I think this was the superior way of doing it. It's very reliant upon how the set command does not allow any duplicates, as well as this really handy constraint up here that always will confirm that it used every digit from 1 through 9. So yeah, I don't really see sets being used all too often, but for questions like this, it is a superb way of finishing the question with relative simplicity. So yeah, that's the way I did it, and I hope this video was useful. So thank you.